Welcome to a look at gas phase work in thermochemistry. In an earlier video, I introduced thermochemistry and internal energy. Let's review briefly. First, in chemistry, we view the universe as two simple parts, the system and the surroundings. The system is the part of the universe that we're interested in, or that we study. This could be a physical process, like a phase change, or a chemical process like a chemical reaction with reactants and products. The surroundings is simply the rest of the universe. This is where we, the observers, record data and observations. Energy can be exchanged between the system and surroundings in the form of work or heat. The energy of the system can be called the internal energy. The internal energy can be classified as the sum of the kinetic and potential energies of the system. But in thermochemistry, we are interested in the change in internal energy. The internal energy can change in the form of work or heat. The change in internal energy, delta E, is equal to W plus Q. Work, represented by the lowercase w, is defined as work acting over a distance. For chemistry students, we can think of work as the transfer of energy in an organized motion. Heat, represented by the lowercase q, is defined as the transfer of energy between objects that results in a temperature difference. Another way to think about this is heat is the transfer of energy in a disorderly motion of molecules. This is called thermal motion. In this video, let's focus on gas phase work. During some chemical reactions, gases can be produced. These gases exert some pressure based on the amount of moles of gas produced, volume of the reaction vessel, and temperature. I'll refer you to my videos on gases for further discussion. Consider the container with a movable piston shown here. A gas can expand and push against the piston and the atmospheric pressure. This is work done by the gas on the surroundings. Conversely, if the pressure of the surroundings is greater than that of the system, work can be done by the surroundings on the gas system. Let's look at the equation for gas phase work. The equation for gas phase work is W is equal to negative pressure times the change in volume, or delta V. The change in volume is the final volume minus the initial volume. The units for this equation are in liters times atmospheres. We can convert these units into units of energy, or joules, by this conversion. 1 liter atmosphere is equal to 101.3 joules. Let's practice using this gas phase work equation. An organic fuel is burned in a reaction cylinder fitted with a movable piston. The initial volume of the cylinder is 0.100 liters, and the final volume is 0.965 liters. The piston expands against a constant pressure of 0.900 atmospheres. Find the work in joules. Let's bring our diagram back. In this example, the gas expands and pushes the piston out. This represents work done by the gas on the surroundings. Since the gas is doing the work, we expect energy lost by the system, thus a negative value for work. Let's insert our values. Work is equal to negative 0.900 atmospheres of pressure times delta V, which is V final minus V initial. 0.965 liters minus 0.100 liters. This equals 0.865 liters. Following significant figures rules, work is equal to negative 0.779 liters times atmospheres. We can finally convert to joules using the conversion factor. The work done by the system is 78.9 joules. We can also say that work equals negative 78.9 joules. The negative sign represents work being done by the system.